Good evening, everyone. Gents, are you there?
I
There you
am
are.
here.
And
Yeah.
John, where are you at?
Working on it, working on it.
Yeah, John is lost in the virtual universe. There he
Hey,
comes.
I'm here.
There he is. Can you guys hear me okay? Because sometimes I have microphone issues.
Yep, you sound good.
All right, great. Well, thank you all for joining us tonight and our friends here on Facebook and on YouTube. I'm Rich Ozer. This is Gerald McKeegan and John Curry. We're here at the Chabot Space and Science Center using the 36-inch research reflecting telescope, fondly known as Nellie, which you can see kind of barely behind me here, just a little corner of it. We have the lights down, of course. The Chabot Space and Science Center is in Oakland, California, and we rely on our community for support. Right now, the Science Center is closed, and although we do have some limited events, private events, in fact, there was just a wedding here today, we do rely on member support, community support, support of the East Bay Astronomical Society, and other astronomy-related organizations around the Bay Area. So if you are so inclined, we ask you to make a donation to us or become a member. And you can go to chabotspace.org to learn about donations or membership, or if you're on Facebook, there is a little red button with a heart at the bottom of your screen, and you can click on that to make a donation. So thank you for that, and I also want to thank Fremont Bank, one of our sponsors and community supporter. Tonight, we're right on the edge of humidity problems, so we're still below our 85%. So there's certainly a good chance that we'll still be able to use the telescope. And before we get started, though, I do want to mention that today's kind of a special day from an astronomy sense. It is the spring equinox. And what that means is that if you traveled down to the equator today because you had nothing much else to do, and you went down to the equator, you would have seen the sun rise exactly in the east and set exactly in the west. And around noontime, it would have been directly overhead. And of course, that happens twice a year. It happens in the summer, in the spring, and it happens in the autumn. And last year, it happened on the 19th. And the reason it happened on a different day last year is because the Gregorian calendar, which we use all over the world, is not particularly accurate with respect to astronomical events. And it is corrected every 4 years when we have a leap year. So the actual time of the equinox has a tendency to drift with respect to the calendar and then is periodically corrected. So anyway, it's Equinox Day. Happy Equinox Day.
It's
Um,
spring.
it's spring.
Yeah,
It
Really
is
feels
spring.
like it here too.
you can tell because we're all bundled up here.
Yeah.
It's just so
How
cold.
would you know? I've been indoors all day. You're right. Yeah. Anyway, that is true. It is spring. Gerald, we have some interesting stuff to show. Before I even came into the observatory, Gerald was already working away, photographing something special. We had actually gotten a request from one of our viewers. So why don't you talk about that a little bit?
Okay. Well, as Richard said, we got a request from a viewer the email request I got as I was looking at the announcement of this event. There is a type of stellar explosion called a nova, not a supernova, but a nova. And a nova just began a couple of nights ago, and it was discovered by a Japanese amateur astronomer. And of course, all the observatories around the world have suddenly turned their telescopes in that direction to watch this object brighten from a barely perceptible star to a star that's outshining most of what's around it. So as Richard said, we've been taking some images, but what I want to do, I'm going to switch to my other computer here and do a screen share, I hope.
Yeah, I think you're set for screen sharing, Gerald.
Yeah,
Let me check.
okay.
Yep.
All right, here we go. There we go. Okay, so this is an image taken by the Digital Sky Survey. It's a sky survey done down at Mount Palomar Observatory in San Diego. I believe they use their 60-inch telescope to do this. And you see a group of stars here. This is in the constellation Cassiopeia. And there's just a whole bunch of stars here. And I want to call your attention to this little star right there. Actually, it looks smeared because there's actually two stars there. This is a binary star system, one star orbiting around the other. Well, it turns out that one of those stars is a white dwarf, and it is close enough to the other star that it has begun pulling matter off of that other star, pulling gas, mostly hydrogen gas, off of that other star and accumulating it in a disk that is around the white dwarf. And that the matter in that disk is slowly falling onto the surface of the white dwarf.
When was this picture taken, Gerald?
This probably a couple of years ago. This is just a reference image that I want to show you.
That's what I thought.
We're gonna blink. Right?
So yeah, we're gonna while you're here for in just a second. So I want to show you an image, give you an idea of what I am talking about here.
The suspense is
So
killing.
there you go. All right. So this is what's happening up there. There's a white dwarf star here. There's a larger star. They're close enough in that the white dwarf is now pulling matter off of the larger star, and it's forming an accretion disk around the white dwarf. And the material in that accretion disk is slowly falling onto the surface of the white dwarf. The white dwarf is extremely hot, but it's what we call degenerate matter. So fusion is no longer happening in the core of the white dwarf like you would see in a regular star. But all this hydrogen is falling onto the surface, and it's getting hotter and hotter and hotter. And eventually it gets hot enough to where very suddenly fusion starts. The hydrogen on the surface begins to fuse into helium, and it does so almost explosively, so that suddenly that little white dwarf there brightens to be as much as 10,000 times its original brightness. So what I want to show you now, let me go back to this one image, that the digital sky survey image. Here it is. Note this bright star here and this kind of pattern of three stars here. And then I said, this is where our nova is occurring. Right now, it's a very faint star, much too faint to see with your naked eye, even hard to see with a camera on a telescope unless you do a long exposure. So what I want to do now is first get all the images of you guys out of the way, and then share a different image. Okay, this is an image we took about 20 minutes ago. Here is that same bright star that I mentioned, kind of that triangle of stars. And here's that star that was very faint in the original image. And as you can see, it has grown tremendously brighter. This is a nova. And it is now at, we measured it a little earlier, it's about magnitude 7.4, maybe a little bit brighter. And we expect it'll get a little bit brighter still in the next couple days. It might even get bright enough to where if you're in a really dark sky location, you might be able to see it with your naked eye. Certainly with a reasonable telescope, you should be able to pick it out. And what will happen is the nova will continue to brighten for a few days, and then it will start to slowly fade over many, many weeks. It will slowly fade out and go back to being like it was. And then maybe 100,000 years from now, it'll do it again. And it'll keep doing this. And each time the mass of the white dwarf increases a little bit more, and a little bit more, and eventually it reaches the right mass and it explodes as a supernova. So this is sort of a precursor, of a leading up event to an eventual supernova, which could happen, a million years from now. But again, this star would have been maybe as bright as this right here, a week ago, but today, as you can see, it's the brightest thing in this image. So that's a nova, and this is getting a lot of attention worldwide. Lots of people are watching it. They're studying it, getting all kinds of data about it. I can show you some other data that people are getting. For example, one thing we do is we analyze the composition of it. And let me share this again. If I can find it, there it is. Okay, so this is spectroscopy that one of the observatories in Japan is doing. Japan is kind of leading the charge with this because it was a Japanese amateur astronomer who discovered it. There's some Japanese observatories, professional observatories, that are keeping track of it and measuring its brightness, measuring the composition. And you see all these helium lines here, these purple lines. Now, this is early on. As it continues, you notice the height of these helium lines as it has continued to brighten. Let me get down here to the next page. You see these lines, purple lines, getting higher and higher, getting stronger and stronger still. And this is because hydrogen is being very rapidly converted into helium on the surface of the star. And that will continue until most of that hydrogen has either been blown back out into space or has been exhausted by the fusion process. So anyway, that's what's going on. It's a really cool event. It's one of those things that happens every once in a while. Maybe every few years we get to see one like this. For those of you who want to try to find it, I've got a star map that I can show you.
Oh, great.
Right here. So this is the constellation Cassiopeia right here. This is the constellation Cepheus. This is where it is located. Now, in this view, it's way too faint. Normally, the star would normally be way too faint to be seen in an image like this. But if you look in this area right now with a pair of binoculars or with a small telescope, you're liable to notice a bright star right to the center there. And that is the nova. And you should be able to view it for the next couple of nights. So, you can't see it with the naked eye, but certainly with a pair of binoculars or with a small telescope. All right. So that's the cool thing that's going on right now out in outer space that all the astronomers are getting excited about. All right.
Yeah, we had gotten a question. Were we looking live through Nellie? No, those are taken about 20 minutes to
half
an hour.
half hour ago.
Half an hour before we started.
I responded to that.
Did you? Yeah. The telescope won't go low enough to hit Cassiopeia right now. It would be really tough.
Yeah, that's it is kind of low in the sky, so you got to do it in the early evening. As soon as it gets dark enough to look in that direction, because Cassiopeia is setting. So by now it would be too low for this telescope to observe. So we had to catch it while we could.
Yep.
All right.
Great. Well, I can go ahead and share my screen, and we can start doing some live feed. How's our humidity doing?
Hang on.
Good question. Let's see here.
Last I looked, it was 82. Still
82.
82.
Yeah.
All
Still
right,
82.
So it's holding. All right.
So where would you like to go first?
Well, first thing I got to do is figure out how to share my screen again because my computer is acting very funny. Here we go.
Computers don't act funny. Come on.
Yeah. It's really the computer operator that's acting kind of funny. All right. You guys see that? Yep. There we go.
Yep. I see Betelgeuse.
That is Betelgeuse. Swimming around a little bit to the right of the bullseye.
So where would you like to go first, Richard?
Well,
you got a couple thoughts?
I gave you a list earlier. Let me.
Yeah, unfortunately, I left a list at home.
Oh, did you really? Really? I've got it. I've got it right here. Fortunately, let's start. Since we were talking about stars, there are some nice globular clusters that we should be able to see. Do you think we can get M3?
Should be able to. It's going to be over in the eastern side of the
Yeah, yeah. We got to
sky.
move east.
So
Go east, young man.
let me do some shifting here. We'll shift eastward and we'll stop off at a few stars along the way to make sure we stay.
Jerem asks, what is the lowest declination Nellie can go to? It's actually not declination that's the limit, but how far above the horizon they can go.
Yeah,
Right.
it's like
Go to about 15 degrees above the horizon.
Yeah, formally 15 degrees, but during the conjunction we took it to 10, and we were scared.
Right.
Are you live?
But
You're not
nothing
live.
fell apart.
Hold on, here we go.
Did we hit it right on?
No, we're not. I'm not seeing it.
Okay.
Which star were you on?
We should be on Procyon. No, okay, I see the problem. Hang on. Okay, we're going east. And maybe a little south. There it is right there.
Something.
Yep.
There we go. We can do a sync.
Bullseye.
Yeah, for those of you who are joining us for the first time, we have to take little hops across the sky and make sure that the telescope is synced up with the visible sky. So when we go to something that is too dim to see naked eye, that will be in the right field. So we take these kind of waypoints along the way.
So let's see. We want to go to M3, which is where? That's down.
While you're doing that, we have a question about that nova. Considering it's light years away, how long ago did this happen? How many light years away did you say it was?
5,500.
5,500. So
Right.
that's when that happened, about 5,500 years ago.
Yeah, so we're seeing what happened 5,500 years ago. I wonder if that's a little too
low.
Too low still. Yeah.
Is the telescope refusing to go there or something? Or
no, it's only 20 degrees above the horizon right now. I was thinking we might. Didn't you mention M95?
Yeah, I mentioned M99, M53, M64, and maybe Ghost of Jupiter were all the different. Sorry about that. That's the sky song. Yeah, I was bringing up my star map.
Okay, M99 is where? It's over by
Coma. It's in the Coma cluster. Coma Berenices.
Yeah, okay.
That's also kind of low.
That's pretty far over too.
Yeah,
How about if we go to like M66 or M65?
That sounds good. Yeah.
Yeah, let's do that. I'll head over to Regulus first and we'll sync on it.
I'd say M65 would be a great target, right? So M65 is a spiral galaxy, and it's at magnitude 9 approximately. So it's a pretty faint object, but we should be able to pick that up.
yeah, this is in the tail of Leo, in case you're wondering.
Yeah. So I see it. Gotta go east a little bit.
It's blue.
Yep, that's Regulus.
That's not M65.
Yeah, that's Regulus, a bright star in constellation Leo.
So we're getting close.
Yep. All right. So let me do a select here. M65, right?
Yep.
And go.
All right. So let me know when you think we're there.
I think we're there.
All right. Let's start with, what do you think, 30 seconds?
Yeah, something like that.
All right. And,
Actually, we're a little off here. Let me move east a little bit.
okay.
Three galaxies right next to each other there.
Yep. That's actually a really popular target to photograph, is all three of them together. Let me know when, Gerald.
Hang on just a second here. Okay, you should be good.
All right, here we go. That didn't work. Hold on. My duration was wrong.
While you're doing that,
yeah, I did this wrong. Hold on, let me get here.
While you're doing that, I'm going to do something over here.
Angela is camping out in Sonoma Coast, or on the Sonoma Coast today, and they brought her, I guess, a fairly new telescope. They're amateurs, and she'd like to know what to look at.
I'd say start with the moon. It's a nice moon tonight.
Yeah.
And that would be a good thing to practice with. You could try the different eyepieces and learn how to point it. And then just to the south of the moon is the constellation Orion, and you can look at the Orion Nebula.
Yeah, nice and bright and easy objects to find.
Yep. All right, so I do see it. It's a little bit off to the right, Gerald.
Okay, let me adjust here. Hang on just a second.
And we'll take another one. And then I'll enhance it a little bit, try to brighten it up.
What you're seeing there in that image is the very center of the galaxy.
Right.
Okay, so we need to move west a little bit. Okay, try it now.
All right, here we go. Yeah, so what John was pointing out is this right here in the crosshairs, the little square, is the core of the galaxy. And if you're watching on a computer, I don't know if you'll see it on a phone, you could see a little bit about the spiral arms extending out. In fact, let me see if I could get that to...
We'll try to enhance that image a little bit so you see more of the spiral arms.
I'm also going to shoot it with the other camera on the finder and see what we get with that.
There we go. That's much better centered now. All right, so I'm going to play with the exposure a little bit, bump it up a little bit.
Apparently, they're still having a little trouble hearing your voice, Richard.
I think your microphone.
Well, what happens is, for some reason, Zoom likes to keep switching which mic is active, and that has been my problem. And that's exactly what happened again. So here we go. That's better.
Oh yeah.
Oh, there you go.
There we go.
Sorry about that, folks.
Now you're blasting our ears out.
Yeah. Now,
you're fine.
Now I'm at normal volume.
Yep.
All right. All right.
So how long's your exposure?
I took a 40-second exposure at a higher ISO this time.
Okay. Okay.
And there we go. And now let me.
So this is one of many spiral galaxies in the constellation Leo. There's a cluster of them there.
All right, there we go. Now we're starting to see a little bit of something here.
Yeah. Oh, there you go.
Oh, that's a nice image.
There we go. So we can see the core now is obviously much more apparent, and you can see some of the spiral.
And that little donut is a speck of dust on your lens.
Yeah, it is.
Or something on your
Well,
tip.
Nellie is my lens, so it's probably
Yeah.
a speck of dust on the sensor. I've been meaning to get in there with a Q-tip for a while, and I haven't been able to do that yet. So yeah, have you tried? Are you trying to take a shot with the CCD?
Yeah, I am. It's not coming out so good on.
Oh, okay. Well,
that smaller aperture, a lot smaller aperture here.
Yeah,
so.
it can be tough. All right, there we go. I'm going to try going to 50 seconds here. Try it again.
Alien smudge. Yeah, good term there.
So this is we've referred to this tonight as a spiral galaxy. There are different classifications of galaxies. There are spiral ones like the Milky Way, where you can see the arms essentially of stars. There are these spirals of stars. There is also something called an elliptical galaxy. An elliptical galaxy is one that has aged long beyond the spiral galaxy phase and has kind of lost its definition, and the stars form a more fuzzy cotton ball like apparition, and you no longer see spiral arms. But let me.
Is this a barred spiral? I can't quite tell from that.
I don't know. We would have to look that up.
Such an angle there, yeah.
I got to get the right. This tool is not the best tool in the world for doing this. There we go.
So one of the things we would do if we wanted to really get a really nice image of this is not just try to take one image at a time, like you see in here. We take a whole bunch of these images and stack them together, manipulate them a little bit electronically to really bring out all the detail. And that's typically, a lot of the images that you see in books and on the internet and so on, where you got this beautiful picture of a galaxy. That's actually not just, one single photograph taken. It's a combination of many photographs taken over a period of time.
Yeah, if I was going to shoot this to do an image that I wanted to, give away or show off, it would be total of like 3 to 5 hours of exposure time.
Right.
And each shot being 5 minutes long, and then I'd stack them all up. But we get a lot done here with just these snapshots sometimes, and it's kind of amazing when you have this much aperture. We'll try this one last shot and then move on to one of the others.
Okay, my 40-second exposure on the other telescope is about done here.
Okay, good. We'll be able to compare.
Yeah.
Uh-oh.
That didn't sound encouraging.
No.
All right, there we go.
Yeah.
All right, that came out a lot better here on mine. You're able to see the definition pretty well now. So it looks like for magnitude 9 objects, we really got to take a full minute.
Yeah, so my 40-second image actually shows less than yours does. I'm using a telescope that has
Yeah.
only 5-inch aperture, whereas Richard is shooting with a 36-inch aperture. And the light gathering capability increases as the square of the increase in diameter. So if you double the diameter, you get 4 times as much light. Going from 5 to 36, that's what, 7 times. So
Something like that, yes.
49 times more
Yeah.
light. 7 times 7 is
Yeah, it's that paradox that 1 14-inch pizza is much bigger than 2 8-inch pizzas. It's the same. You have to do the
Same
math.
concept exactly. Yeah.
that what I'm doing wrong.
That's what you're doing. We're comparing. Actually, I'm hungry. That's what I'm thinking of pizzas.
All right.
All right,
Okay.
so that's not bad
That,
though for a minute,
that,
and
that worked
we
out.
can move on.
All right.
Yeah.
Let's see. Where else should we go to?
Well, do you want to look at one of the other
try
galaxies?
M99 now? You want to try that?
Yeah. Let's give that a
because
shot.
it's a little higher now.
Yeah.
Okay. Let's.
It's another beautiful spiral galaxy. So
I'm gonna slew on over to the Nebula to synchronize.
Okay. I'll put it on live view.
Yeah, that's pretty close.
This one is much more perpendicular, sort of.
Yep.
Yeah, much better view of the spiral arms, if we can get a good picture.
Yeah, I mean, we're going to have to take a full minute on this one for sure.
Yeah. M99, that comes out of after 98, right? Yeah, there we go.
Yeah.
Depends. So we're not doing the marathon tonight.
Yeah, that's right. We're still tired from that. So this is in Coma Berenices, or Bernice's hair, right? Yeah. All right, are we there?
We're there.
All right, I will, this is our previous image, obviously. I am going to shoot the same exposure because it's roughly the same magnitude. And when I say magnitude, that's the astronomy term for brightness. And the higher the number, the dimmer it is. Just like everything else in astronomy, it's counterintuitive.
Backwards, yeah.
Yeah.
Yep. We want to keep you guessing.
That's right.
If you found out how simple some of this stuff was, then everybody would be doing it.
Well, we did the pizza comparison before. We've
Right.
given it all away now.
Well, that's the most. That seems really obvious to me. So yeah, higher numbers mean dimmer. Oxygen is a metal. all of those things about astronomy. You have to learn a whole new point of view.
So how long are you doing? A full minute?
I tried a full minute because it wasn't worth doing shorter exposures on the other one, so might as well do the full minute.
I have a question: is the Hubble telescope still sending back pictures?
Yeah, they had a problem this week though. There was some issue.
They had a glitch, but they fixed it. It's back in service.
It went into safe mode. There was some problem that came up with the gyro control, and so it shut itself down.
It was probably a Microsoft update.
Yeah,
caused it to go into.
Yeah, of course it was. All right, so there we go.
Yeah, that looks pretty good.
Let me get it just a tad. There we go.
I can see some spirals in there.
Yeah, I'm going to take it.
This is called the Pinwheel Galaxy, the Pinwheel Nebula. One of them.
One of them.
Yeah. I'm going to take one a little bit longer. We'll see what happens. So this one, like the other one, is a spiral galaxy, but what's different about it is its orientation with respect to us, right? So the last galaxy we looked at is probably very similar looking in that it has this these widespread spiral arms, but the plane of the previous galaxy was more perpendicular to our point of view.
This one is. Yeah.
This one is face on. I mean, more parallel to our point of view.
Yeah.
This one is more perpendicular.
Right. The other one was almost, well, not quite, but almost edge on.
Yeah.
Gerald, you've got a request to try 120-second exposure of this on the CCD camera.
Oh, yeah? Okay. Ask and you shall receive.
Yeah, give it a shot, man. Why not? Okay, so got a little more brightness there.
Germ says as far as the Hubble is concerned, they had to unplug it and plug it back in again.
That's pretty much what they did. That is an accurate description. All right, that's not too bad. There we go.
Yeah, that's pretty good.
Yeah.
I like it.
Yep. I'm not going to toy with it much more. Yeah, this tool. In fact, I'm thinking of sending the developer a request that they kind of enhance that little tool to give you the option to make it bigger, so that small motions don't change it quite as dramatically. So you have a little bit more dragging room, and I wonder if he would do that. This piece of software is developed by a very nice person, so he'll listen.
Yeah, it never hurts to ask.
Company in Canada called O Telescope.
One of the things I wanted to point out, and this is true of almost all spiral galaxies, there are only two main spiral arms, one coming off of either side, but they wrap around the core of the galaxy, and the extent to which they wrap around actually defines the classification of the spiral galaxy. We have different classifications based on how far wrapped around the spiral arms go. The other thing that happens is sometimes the spiral arms develop spurs, and you can actually see one.
Yeah, you can see that here, right here.
Right.
There's
nice. So there's
this
the main
arm
one.
is there's the main one coming off like this, but you can see that there's another one that goes off like this, and it's a split right here.
Right. Well, the problem with the 120-second exposure is with this camera we have to do a dark exposure. So
oh yeah, so it's actually 240 seconds.
2 minutes of dark exposure and then 2 minutes of light exposure.
Yeah, that's kind of why we do the DSLR thing for most of the program. Is that it starts when you have more sensitive instruments, it starts to get more complicated real quick. But yeah, I'm going to see if I could do something about that dust bunny on there. So for the future programs.
Well, yeah, you got an offer from Richard on that one to go see him. He's got cleaning stuff for you.
Oh, Rich Navarrete?
Yes.
Oh, I may take you up on that, Rich. That would be great.
Yeah,
I'll get in touch with you during the week.
Try it with a little air first, one of the little squeeze bulb, and just.
Well, I'm gonna see if I could see it.
Yeah.
First, and then if that doesn't work, I'll just drop it in a pot of boiling water and see what happens.
There you go.
Yeah. Right. Okay.
Yeah. And then stick it in rice after that, right?
Yeah. And that will give me an excuse to get that one that Rick has.
Okay, well, we're halfway through the 120-second light exposure with the other camera. So.
Well, I might as well take another one here.
Yeah, really. I think you'll be done before I am.
Yeah, mine is 70 seconds.
Yeah. So in case you haven't figured it out by now, astronomy is, especially when you're doing astrophotography like this, it's a whole lot of time spent hurrying up and waiting.
Yes.
Yeah.
A lot of patience involved.
Yeah.
Well, the real game for when you have your own setup and you're doing astrophotography, you are really accomplished if you can keep the exposures going while you're taking a nap.
Yeah.
then you really have got it down.
And that's one of the nice things about the software that Richard is using. He can program it to just take multiple exposures using the same exposure length and settings and everything, and then walk away and just let the camera do its thing and the computer do its thing. And like he says, go take a nap.
And you're presuming at that point that the guiding is working well, because you also have robotic guiding going on, and that the focus isn't changing dramatically. So all of those factors come into play.
My 120-second image is pretty disappointing, guys.
Well, let's look at it. Let's look at it.
I'm embarrassed to look.
Don't look.
You were requested to show it.
Come on, Gerald. Think of all the horrible images I've been showing the audience.
All right, I'm going to share here.
Several months.
This is embarrassing.
That's not embarrassing at all.
Yeah, there it is.
Oh, that's actually a pretty good picture.
That's actually pretty good. You can see the spiral arms really well, and you can see that split that we were talking about in the 10 o'clock position on the galaxy.
And over here is a really bright star that has actually saturated the pixels.
Yeah.
Camera.
Well, we're not expecting.
That's all right. You can crop that right out of the picture. Don't worry about it.
No, that's great, because it really does show the structure better than the color image does, because you got more contrast.
A little bit. We should do M51. That'll show up really well.
Yeah.
Get the whole thing in there too. Both galaxies.
Okay. So
cool. Good job, man.
So what's next?
Let's see.
The moon's up.
You want to do the moon. All right.
And I won't be doing that with this camera. It'll just saturate it.
Yeah. Use your CCD camera on the moon.
Yeah.
Let's see. I want to see what else we've got going on here in the coma cluster, because I was thinking, if we do want to look at a globular, we could look at M53. And that's at about the same elevation as what we were just looking at.
Okay.
So I think we should show people a globular cluster if there's some available. So let's see if M53 is high enough.
What we can do here. Yeah, I think it is. Let me synchronize first. And then go over here to M53. Stand by.
All right.
Yeah, it should be. I can see Arcturus already, so it's above that.
Let me know when.
I believe we are there.
Okay, well, we'll find out. All right, 30-second exposure. So M53 is what we call a globular cluster. And when we're talking about clusters, usually we're talking about star clusters, although there are galaxy clusters also. But star clusters come in a few different forms, the most notable being open clusters, and the other being globular clusters. Now, globular clusters consist of hundreds of thousands of stars. That's frequently the case, whereas open clusters may be as few as a half a dozen stars, going up to maybe a couple hundred. So this is a globular cluster, and you need to bring it down a little bit.
Yeah. Why don't you give me live view here? I can't see it, so.
I don't know if you'll be able to see it live view, will you?
Oh, am I not sharing?
No.
Oh, got it. Well, that's not going to work.
So I don't know which direction to go here.
Bear with me. No wonder I see you on the Zoom screen and not the cluster. Here we go.
Well, I am a cluster, but
that's
we won't go there. We won't go.
The Gerald cluster, but yeah.
Okay, try it now.
All right, let's do another shot.
In the meantime, Joan says we love our globular clusters. Yes, we do.
Yes. So globular clusters are very old stars, consist usually of first generation and maybe first and some second generation stars. And we know this by looking at the spectral lines that are seen using a spectroscopy tools, and we'll see that they don't have the same composition of heavier elements as newer stars like our own sun. So these stars may be as old as 12, 13, 14 billion years in age. Let me reset this.
And there's a whole lot
There
of
we
them
go.
in the cluster. These things
Yeah.
are upward of several 100,000 stars.
There we go.
The stars are orbiting around the center of the cluster, and then the cluster orbits around our galaxy in a region called the halo. The halo is kind of a nearly spherical bubble, if you will, that surrounds the Milky Way galaxy. The Milky Way galaxy is a spiral galaxy, so it's like a flat disk with spiral arms in it and a central bulge. And around this, that is this region called the halo. And the halo is full of old stars and globular star clusters like this. And we think that there's also that this is actually part of the cloud of gas and dust when the galaxy was first forming. And there's also a lot of dark matter out there too.
Now, this particular globular cluster seems to have a interesting selection of different colored stars, whereas some don't have as many red stars. This has a lot of red stars, it seems, and usually I'm not seeing that many. Usually it's more the white
Did you
ones.
lose your focus a little bit on that?
I think it might be a little soft. So next time we hit a guide star or a waypoint star, we'll refocus.
Okay.
Great.
All right. So, like we say, there's about 150 of these, and we're just getting into the part of the year when we get a lot of globular star clusters like this. If you were with us last week when we did the Messier Marathon, I think there's something like 20 or 21 globular star clusters in Messier's catalog. We showed every single one of them. And you probably were thinking, gee, they just keep showing the same image over and over again. But actually, there are differences.
It did kind of seem that way when we were doing it. We should be able to, maybe we'll be able to see Ghost of Jupiter, or is it behind Rachel's Dome?
Let's see.
I think it might be behind Rachel's Dome.
Yeah, we may have to wait a little while.
Yeah, we're gonna have to wait on that. All right, sorry about that.
Yeah.
Right,
let's see what else we got up here. We got a whole bunch of galaxies in Coma Berenices.
We could do M99. I don't think we did that yet.
We also have M3. We could look at M3. It's another.
Oh, there we go. Yep.
Another globular.
Can we hit a waypoint star to adjust focus before we do
All
that?
right. Let's see here. Let me go back to this one. You want something that's not so bright.
Yeah, not super bright. Medium brightness would be best.
Okay.
Oh, our humidity has gone down.
Good.
We're doing good here.
Well, whoever arranged that, thank you.
Yep.
Must have been one of our viewers.
Yeah, well, maybe Germ brought up the lower humidity.
Okay, let's get that down where you can zero in on it.
Okay. You can get that right in the center for me on the big one. Good. Now,
okay.
Let's see if I can get that better. So it's at 14, 13, 12. Yeah, it's better right there.
Here you go.
Hold on. Let me... All right, I gotta go back the other way for a sec here. All right, that's as good as I'm going to get it.
Okay. All right. You ready to slew to M3?
Let me hook this on here. There we go.
I think Ghost of Jupiter might be actually doable in a few minutes here.
Good. Okay.
About
Well,
27 degrees up, and I think the top of the dome over there is a little less than that.
all right. Well, let's do M3 first, and
Sure.
All right. Slewing.
okay. All right.
Oh, how long you doing?
30 seconds.
Okay.
That seems to be the right amount for globular clusters on this camera. The magic globular cluster number.
The formula for a globular cluster.
Yeah, it's 30.
30 seconds. Gee, that looks like just like the other one.
We'll see.
So the stars that you can still see in the globular cluster, those are very old stars.
Oh, there. That's a much better example, right?
Yeah, that's sharper too.
Much sharper. Yeah, thank you,
Yeah.
John, for pointing out the soft focus because
Good.
it makes a big difference. Yeah, great. And again, you can see the different types of stars here pretty obviously. You got the kind of the orange ones and the white ones.
And you may see a few blue ones. Occasionally, what happens because these stars are so close together, they occasionally bump into each other or get so close that one star strips gas off of the other and exposes its hotter interior. And hotter stars are bluish white in color. But since these are all old stars, it first confused astronomers. How could there be bluish stars? Blue stars are typically very massive, very hot stars that don't last very long. So how can there be blue stars in these globular star clusters? Well, it turns out it's either because a couple of stars collided and the combined mass now made them hotter stars, or because they had their outer layers stripped off, exposing the hotter interior of the stars. So we call them blue stragglers, and we see them occasionally in globular star clusters. Now you notice there's a lot of yellow stars in there, and that's because those stars are low mass stars. Most of these stars are actually lower in mass than our sun. So maybe only 80% of the mass of the sun. And that's what allows them to live so long, allows them to hang around for 10, 15, 20 billion years. So some of these stars will still be there long after our sun is gone.
Great.
All right. So where are we going now?
We were going to try Ghost of Jupiter.
Okay. Is there a waypoint we can go to along the way?
Let me see. It's a ways away, so we're going to need it.
Let's see here.
Because it's in.
Well, I'll kind of work my way over there. I'm going to go back to
Hydra.
Yeah.
So you might want to consider
Alphard
doing like the Nebula.
Okay, I was actually going to go all the way to Rigel
or even Regulus. Yeah, Regulus will work.
Yeah. I'm going to go to Regulus here. That'll be a nice bright star. We can
all right.
See it. So give me live view again.
Yep.
You might go to Alphard, Alphard, Alphard. It's also in Hydra, and it's much closer.
Yeah.
Yeah. Yeah, that's actually makes sense. It's above.
Well, let me get this one.
Which one is this?
This is Regulus.
Oh, it's Regulus. Okay.
Yeah, so we'll sync on that. And then slide on over here. And maybe go to Sirius next, or Betelgeuse. How about Betelgeuse?
No, that's
Um,
way too far the
No,
other way.
Too far?
You don't want to go that way.
Go to Alphard. That's a
Yeah.
that's a good one to do. ALPHARD.
Okay, hang on. Okay, here we go.
Well, that's not bad. All
Well,
right.
not too far off.
No, pretty
All
good.
right, let me
Wait.
readjust here.
Yeah, okay. I thought you were going to sink.
Sink or swim. And then the last jump, we got to go east to Ghost of Jupiter.
Okay, does it have an NGC number or something like
You
that?
know,
Yeah, it does. NGC 3242.
Oh, thank you,
Okay.
because it doesn't show up on the sky for some reason.
NGC 32
3242.
42. Okay. Oh, actually, it does show it on here.
That's funny. On mine, it doesn't. I don't know why. Oh, it does when I hover over it. There we go.
Okay, going, and we're there.
All right, let's do a my usual 30-second image.
So, Ghost of Jupiter is not a planet. It's not a ghost.
Or a ghost.
Yeah.
It's actually what we call a planetary nebula. And the word planetary doesn't mean it's a planet. Planetary nebulae are the remnants of dying stars. Most stars die in a very slow process where they swell up and then they shed their outer layers. And then eventually whatever's left of the star kind of collapses into what's called a white dwarf. The white dwarf is surrounded by all the gas that it was shedding for hundreds of thousands of years before it became a white dwarf. And the white dwarf is extremely hot. It puts out a lot of ultraviolet radiation, which goes out and ionizes the gas that it was shedding before it became a white dwarf. And so what you see here is ionized gas surrounding the white dwarf. That little dot in the center is the white dwarf. You can see a shock wave. This does not happen in a nice, smooth, continuous process. It happens in episodes and fits. And so you get shock waves, and you can actually see a shock wave propagating out within the cloud. And this is what's going to happen to our sun in about 6 billion years.
Now, this particular planetary nebula has always been a fun target for amateur astronomers because it has such a notable color to it, right? It's like when you look at different planetary nebula, they either have a really interesting shape or they have a very interesting color. And this one is just well known for its deep blue color. And that's because of the presence of oxygen. And we've talked about that in previous weeks, how planetary nebula glow in various different colors, with red being the hydrogen that has been thrown off from the star, and the blue being the oxygen. And although there's plenty of hydrogen here, in fact, there's mostly hydrogen here, there is enough oxygen to give off that blue light that overwhelms the dimmer red light given off by the hydrogen. So even though there's less oxygen, it glows brighter.
I have a quick reply here. Somebody asked about Rachel not knowing what we were talking about.
Oh, yeah.
Rachel is, we name all of our telescopes here. And Rachel is our 20-inch refracting telescope. And its dome is right next to us. So we have to make sure that objects...
Thought we had some woman standing outside.
Yeah. I would think that would kind of sound kind of strange for somebody who had no idea what we were talking about. Rachel, get out of the way. You know? Yeah, no, Rachel has a very tall dome, and because it's a very, very long telescope, so it blocks part of our southeast sky.
Yeah, yeah.
All right. Well, I'm going to take one more shot here. Just might as well. I really enjoy looking at it.
So if you have any other questions, feel free to jump right in there and shoot them at us. We thrive on those questions.
We did have one question about the magnification of what we're looking at, and that's probably not a terribly easy answer in this case.
Because I'm also digitally magnifying it. If I reset this to what it actually looked like off of the sensor, you'll see that this was the full frame, right? But I realized there was enough detail there to magnify it. And
so in the full frame image, you probably are magnified around 200 times.
Yeah. And then there's, then we have to think about what the natural magnification is of Nellie at prime focus, which is what we're doing here.
I have that number somewhere, but I don't have it here.
So the way this is set up is, Nellie has the 36-inch mirror at the back of the telescope, and the image from that mirror is bounced off of a secondary mirror that's towards the front of the telescope, and then it goes back to the camera, and the camera does not have a camera lens on it. It just has a tube on it that allows me to attach it to the focuser. There's no intermediate optic like an eyepiece or a Canon lens or anything like that. Not to say that we can't do something like that, but typically you just put the sensor at the focus, and that's what we're doing.
Want to minimize the amount of glass that the light
has
to go
that's
through.
Exactly right, because with every piece of glass, there's some additional distortion that's introduced.
And reflection that loses some of the light.
Yes. Yeah, the reflection can be really annoying. That could be even worse. Sometimes you'll see two of whatever you're looking at.
Somebody thought Rachel was a constellation.
That's even better. We should name a constellation after.
Yeah,
Rachel.
we should.
I kind of like that. Yeah, so we have
Get
Rachel
the IAU to do that for us.
Yeah.
So to answer the question though about magnification, normally if you're looking through a telescope with an eyepiece, there is a way to figure out the magnification, and it's a relatively simple formula. The telescope itself has a focal length. If you took the eyepiece off and you held a piece of paper in front of the back end of the telescope and moved the paper around, you'd find a point where the image is in focus on the piece of paper. And the distance from there to the primary lens or the primary mirror is the focal length of the telescope. So with this telescope here, that focal length is about 1,715 millimeters. 7,000.
315. There you go.
It's been a long time since I did this. 7,315 millimeters, 7.3 meters. Right. So then you have an eyepiece, and the eyepiece also has a focal length. So typically we might have an eyepiece of, say, 35 millimeters. So what we do is we take the focal length of the telescope and we divide it by the focal length of the eyepiece, and that gives us the magnification of the telescope.
Jari was mentioning something really interesting. There was a news story about this very high resolution mosaic of the Milky Way that was done by an astrophotographer, and I took a look at it. It is quite amazing. It's one of the best high res.
This is not Axel Mellinger's image, is it?
No, the gentleman's name is a little bit hard to pronounce, and I would ruin it. I was fortunate to have lunch with him a couple of years ago at the Astro Imaging Conference, and one of the things he explained to me is that he does all of his work in Norway, and it is often cloudy, and it is also very, very cold. It can be minus 10, minus 20, and that's probably one of the reasons it took so long to acquire all of this data, and because he had a lot of cloudy nights to fight with. Fortunately, he's able to control his telescope from indoors where it's warm, so he doesn't have to sit in the 20 below zero.
So if you're interested,
temperature.
Take a look at the comments section. He provided a link there, and go ahead and follow that link, and you'll.
Yeah, that was first done. Bob Schalk just pointed out that you can see at the 7 o'clock position in this image of the ghost of Jupiter, you can see a change in the shock wave. There's kind of a bright spot there.
Right here.
Right there, yeah. So anyway, talking about taking the picture of the entire Milky Way, you know, we're inside of the Milky Way galaxy, so it's kind of hard to get a picture of the whole Milky Way galaxy.
Kind of impossible.
It's like it would be like standing inside your house and somebody wanting to say, take a picture of your whole house.
Yeah.
Several years ago, a German amateur astrophotographer named Axel Mellinger did it. And what he did is he traveled to different places around the world, northern hemisphere and southern hemisphere, to all kinds of different points where he could see the whole breadth of the Milky Way from, you know, all these different points. And then he pieced them all together, and it was a lot of processing because he had to get all the images to be this, you know, this exact same exposure and get them all pieced together so that they matched up correctly and everything. And he ended up with this beautiful image of the whole disk of the Milky Way seen edge on, because we're inside of it. But you could see the central bulge, and you could see all the way out to either edge of the Milky Way. It's really tremendous image. And he was up here at Chabot several years ago. He and Conrad are actually friends. So that was pretty spectacular.
Yeah, it sounds very interesting.
Yeah. In fact, I wonder if I have his image. I wouldn't be at all surprised if I do.
So you'll notice that I'm sneaking in all of these 30-second shots while Gerald is talking.
And you're going to amaze us when we're all done here.
Yeah, it means next week I'll show you a processed image of the ghost of Jupiter.
It actually looks pretty good considering the breeze here tonight.
I know,
it's pretty good.
Fine. It'll be fine. I'll be able to give you something.
Well, I've got one that was done by the European Southern Observatory. So maybe...
Well, if you search for Milky Way Mosaic or follow the link, if you go to astroanarchy.blogspot.com, you'll see his mosaic.
So I'm sharing it right now. This is this is what the European Southern Observatory. They did this. So here's the central bulge of our galaxy, and here's, you know, the disk of the galaxy right here. One thing you want to notice, though, is you can see a slight bend to it. One of the interesting things about our galaxy is it's slightly bent, more so on one side than on the other, and that's kind of unusual.
That's not due to us being inside one of the arms and.
No, it's actually been confirmed that there is a bend to our galaxy. Now, we've seen that in a few other spiral galaxies, but it's not real common. And so that's an unusual feature. And these things down here, these are the Magellanic Clouds right here. Those are sort of dwarf galaxies. They're gravitationally bound to the Milky Way. Pretty cool.
That is a nice.
Yeah, that's a great
interesting image.
All right, back to your image there, Richard.
All right, let me see.
Let's see, we're a little after 10 o'clock now.
Yeah, we're.
So, folks, if you got questions, now's the time to fire away. We'll be glad to answer them if we know the answers. If we don't know the answers, we'll just make one up.
You know, I was actually thinking, you know, when you were talking about, well, this isn't a planet and it isn't a ghost. And then I was really thinking about how astronomers really hold on to the words and terminology from eras past,
Yeah.
right?
Yeah.
So
Yeah.
it just won't let go of it, and it creates a certain amount of confusion, but it's also kind of fun.
Yeah.
Yeah.
Ages ago, everything was a nebula because they didn't know what it was. So we didn't know whether there were galaxies or what, but everything was called a nebula, or almost everything.
So Colby asks if there's a possibility that we could collaborate with other observatories around the world to get different shots and do it all in our live stream.
Wow.
Well, I've been thinking about that. It's actually kind of tough to do because we use Zoom, and that gets broadcast to an intermediate service that then splits the broadcast to YouTube and Facebook, and to somehow combine that with another Zoom feed or another feed is really tough. They would have to be able to split their feed as well, and somehow combine it with ours. And we haven't really figured out an easy way to do it that's going to work.
But not only that, but on the other side of the world, it's daytime.
Yeah, that too.
Right.
Well, there is that.
And we have to get them to coordinate everything with us.
Yeah. There is that.
Yeah.
But that's kind of a technical problem that's not easily overcome without a lot of new software being involved.
So it looks like somebody just joined us and is asking, what is that? That is called the Ghost of Jupiter. It's a planetary nebula. It's actually the remnant of a dying star. It has nothing to do with planets.
All right. Well,
Bob Schalk is asking, what about a carbon star?
Yeah.
Do we have any close by?
Oh.
That is a great question. Well, there is always Wolf. Isn't Wolf 35? No, that's a Wolf-Rayet star. So
yeah,
there's Wolf 359.
Is no, it's getting too low. I was going to say that one in Lepus.
Yeah, that's too low.
It's too low. Yeah.
Let me see where. 359.
Hang on just a second here.
Yeah, I don't have the spectrum on that one, so.
Yeah, so Bob Schalk, who used to be part of the Chabot crowd here, he is asking about a carbon star. A carbon star is a low mass star that is fusing helium into carbon, and the carbon is getting churned up into the upper part of the star's atmosphere or its upper layers of gas, and it's actually blocking some of the light that's coming from the interior of the star, and it gives it kind of a reddish hue. And it's very interesting to see it because you don't expect a star to be as red as these stars are. And they're called carbon stars for that reason.
There is one in Leo called CW Leonis. It's a really well-known one, but it's magnitude 10, but we should be able to see it.
CW Leonis?
Yeah, and I can give you the... hold on here. Let me find it.
There's also one in Hydra.
What's the magnitude?
6 to 12.
Oh, that's better. That's better.
Well, depends.
Well, it's probably
variable star, right?
Yeah. But the CW Leonis is 10 to 14, so I think the odds are better with your Hydra one.
It's a V Hydra. I'll have to look up.
Yeah, we'll have to get
SAO number or.
Well, not on this list, but that's what I'm looking for here. Hang on.
V Hydra.
Is that DRAE?
Yeah, Yeah, let me see.
HYDRAE. Yeah.
Can't find an SAO number on it. Why
That
don't they do
says
that?
V hydrate doesn't
Oh,
work.
here we go. I've got to hit Parcos number.
That'll work.
HIP 53085.
HIP 5
3085.
3085.
Yeah, I've got a SAO if that doesn't work too.
Oh,
Yep,
good.
it likes it. All right, here we
Okay.
go.
All right, I'm going to put it in live view just for the moment here.
For you, Bob, anything.
Yeah, pretty much.
As long as you come and clean our telescope once in a while. I think Rachel's due for cleaning.
Did we explain what a carbon
Okay,
star is?
we should be there. Yeah.
All right, let me
did.
go ahead and take a shot now. I'm going to actually take a shorter one to start with and see if we can get it in 15 seconds. So this is in the constellation Hydra. And so for all of you Marvel fans, hail Hydra. Let's see if we got anything. Yeah, there we go.
Yeah,
That's pretty bright.
it is.
That's a
we're
nice bright carbon
little
star.
off. Let me go a little north, and you can maybe
Yeah.
shoot another one. Okay. Try
All
it
right,
again.
you ready? Looks like that's about
Yep.
the right exposure too. So
Yeah, so you see the color. I mean, this is nothing like any of the other stars we've been looking at tonight. It's in this image, it looks kind of orange.
Yeah, sometimes they get even redder than that. They get
Yes, yeah, especially when you're looking
deep
with
red.
the naked eye through the telescope. These things can have a really red color. And again, it's carbon that's being churned up from the interior of the star. Yep, I overshot.
you overshot it. Yeah.
All right. Sorry
It's nice.
about that.
Yeah, that's okay.
Of course, you're magnified a little bit too. So.
You're right. Let me see if I go down one. Yeah, they could just leave it there. This is
Yeah,
fine.
that looks good.
This gets the idea across, and you can compare it to the other stars in the field that way.
So carbon is being churned up from the interior of the star. So the outer layers of the star's gaseous envelope has a lot of carbon in it, and the carbon absorbs a lot of light. It's just like having, a lot of soot in the air. If some of you remember last year when we had all that smoke in the air here in the Bay Area, and the whole sky looked orange. That's what's going on here. It's just absorbing a lot of the light. It absorbs more of the blue and the green light than it does the red light. And so we get this orangish, reddish color. And that's called a carbon star. All right.
Yeah.
Okay.
That's
You
a pretty
asked
good
Bob,
place.
and we
You asked for it, you
delivered.
got it.
We delivered.
That's probably the first time we've been able to do 2 special requests in one night. So
Right.
I'm
Yeah.
really pleased.
All right.
Completely unplanned. Not bad.
Yeah. As you could tell, it was completely unplanned.
Yeah, most of what we do is completely
Yeah,
unplanned.
it pretty much is. But, it was a little more so, and it was hard tonight because it's cold and our brains are frozen.
Right.
And it's like-
Okay, well, I think we're at 10:18 here, so I think we ought to wrap it up.
Yeah.
Once again, I want to remind everybody we do rely on your donations because our museum is closed right now. So if you wouldn't mind clicking on that donate button on Facebook or go to Chabot's website, chabotspace.org. And you'll see a donate button at the top of the web page there. Just click on that button and give us a donation. We'd really appreciate it. We want to keep doing all this virtual programming here. And we're also getting the facility ready for when we can finally reopen later on this year. So help us out with a little donation. We really appreciate it.
We certainly would.
All right.
one good question before we split. Are the colors from the carbon star and Jupiter's ghost natural colors, that is, unenhanced in any way? Yes, you were seeing them straight off the sensor. We don't have the time or the software involved in our presentations here to do any type of enhancement or color changes. So,
Yeah, it looks pretty cool the way it is
yeah, it
anyway,
is. Yeah,
Right.
why would we? That's right. So anyway, that should do it.
All right.
All right, you
Okay.
guys have a nice weekend. What's left of it? Got another day, and we'll see you next week. And stay well, everyone.
All right.
Okay. Good night, everybody.
Good night.